of us is about the product, system, and the digital twins. So Anna and we are the chair of the whole session. We will help to chairing the whole process, make everything work. So in the morning session, actually we have 5 presenter and 1 panel discussion. The host of the panel discussion will be the Alejandro. So okay, so let's start for our first session. Okay, so everything is fine online, right? Can you hear us?
Yes.
Okay, good. So for the first presentation I will introduce the IOF Systems Engineering Working Group. As the Sun introduced, in IOF we have several working groups. So for systems engineering part, actually we have a specific systems engineering working group for our session for the systems engineering and the model-based systems engineering. So I will introduce the content for this presentation. The first thing is I will introduce the current status, and then we will introduce some achievements, and then some demo in some European project and some future work we hope to do. First thing is that I want to introduce the scope for the whole systems engineering working group. As we know now, the digital twin is very famous in other industries, right? So totally speaking, the digital twins is always have 2 parts. The first part is physical entity. Another part is virtual entity. But based on our research or some survey for the industry and the academia paper, then we found sometimes some type of model may be also used for system life cycle to manage the complexity to support the system development for the system life cycle. So from our understanding, currently in our systems engineering working group, we hope to have 2 main parts. The first part is focusing on the physical entities in the industry, in the real world. Another part is for system life cycle from the systems engineering aspect to consider how to define all the information related to the physical entities. Also, in the virtual entity part, as we know, we already have a lot of DD model, RTI model, information model, operational model, performance model anyway. So we also trying to find some way, trying to formalize all these virtual entities at the same time. So in current approach, we use the BFO and IF core as our core specification as the top level ontology. Then at the same time, we have made separate this ontology as 2 parts. One is IF systems engineering ontology in order to represent physical entity system life cycle. Another one is about model-based systems engineering ontology, trying to use some ontology to represent the virtual entities as we already have in this finger. So based on the roadmap, we already, because our working group is a very new working group right now, but so based on the roadmap, we have 2 roles in order to realize our target. The first part is about the system architecture. We're trying to understand what is system architecture, what is viewpoint, in order to understand how to use ontology to represent the system engineering, and others. Another aspect is that we propose some initial idea about how to define the MBSE models. So we have some papers, some case study, and has already used in Airbus in some other European project. I will introduce something later. So in this situation, we have these 2 roadmaps, in order to define the systems engineering ontology and the model-based systems engineering ontology. So I will have a very short introduction about the systems engineering ontology because we don't have enough time. After about 1 year discussion, now we already have 40 class about the systems. And actually, also, we already defined 1 scenario in order to evaluate the 40 class. But now the challenging thing for us is that it's very difficult to define the hierarchy between system, subsystem. So yeah, this job is is still we still develop this job in order trying to find some solution to do this. But if everyone others you are interested in what we are doing, so join in our working group, then we can continue discuss about it. And so next part is that MBSE ontology. Actually, we already defined three classes. So based on the three basic classes, like we use the MOS, the modeling framework, as the meta model, and the model, and the system life cycle, like some system something. So we already use, based on these three classes, actually we can define the meta model, meta model, and the model, and some example will be introduced later. And also based on the concept that we propose, like a graph, object, relationship, role, point, and a property, we can use all these ontology concepts to represent the model, the MBSE models, MBSE meta models, something, yeah. So current achievement, this is not all the papers on conference because we don't have enough space to put everything. But based on some proposed idea, this is the paper to introduce how the GeoPPRE ontology works to represent the MBSE models. And we also have some other papers based on the GeoPPR ontology to support the code simulation, to support the system modeling, to support system simulation, and also we investigate MBSE, the whole MBSE domains. About 4,000 paper are investigated, and also we propose some new concept about the cognitive digital twin based on the ontology we propose. And in this paper, we introduce one approach is that we use the MBSE to support the system development. Then we use OWL. We use the ontology we design to support the AI integrated with the MBSE. So demo. So based on the ontology we propose, as we want to introduce our approach to other community and other European project and Chinese project. So now we already have some achievement. The first one is MetaGraph 2.0. This is a modeling tool which can support this GeoPPRE approach. And EPFL, we work with some other partners. We hope to develop some open source modeling tool which can be used for the whole community and maybe the whole engineer, not only in China, European, US. So this is the second software we are developing. The third one is that currently there's one SysML modeling tool in China. They're trying to transform their SysML model to the ontology model. So this three tool is developed. And in one Fontolog project, in a European project Fontolog, there's also a PSM, a PIN simulation model, which hope to support this GeoPPRE ontology. And for project, currently we have quality Fontolog and some Chinese national project. They hope to use the standard we propose. And the first example is from Airbus. So we see the video in the lab. We already see the video, but Xiaochen will introduce this demo in detail later in the presentation. And another is that a BRC, the BRC demo. So we use MBSE, the architecture model, to define all the development process of the meta forming process in BRC. Then they transform the architecture model to the OWL model we design, and then use the OWL model. They continue to generate the Patrinet model to run the simulation to verify the performance of the whole meta forming process. Another one is that they use the similar approach to support Huawei, the autonomous driving system architecture design. And all these architecture, including requirement and design structure metrics, are generated into the ontology model based on the we propose. then this ontology currently we are trying to understand how to use this ontology, and maybe this ontology will be integrated with some AR, some technology in the future. And the third one is in our European project quality in Ontology, and this is develop some. They hope to develop one IoT platform for 5 panels, including different industries. So what we are doing is that we use our ontology to help them to define the knowledge model and to support the anomaly detection, and then visualize them, integrate the data to their IoT platform. And the next step is that we are hoping to use the MBSE approach to generate the knowledge graph model automatically in order to realize this IoT platform can be developed automatically. So the future work. So actually, I don't introduce so much information about the future work. So, but based on the papers for MBSE domain since 1993, we investigate about 4,000 or more papers here. So why I say ontology is systems engineering in the future. So you can see now in the factorial analysis, you can see ontology is here, is in the very centric place of the main topic of MBSE. And another tendency is that, you can see this finger, actually based on the paper analysis, we can know, okay, so in 1993, the first researcher, they proposed MBSE, they proposed, okay, systems engineering is important. Then in 2007 and 2017, so you can see still, they think systems engineering is very important in the MBSE domain. But in the last 3 years, you see the tendency is from systems engineering to ontology. So that's why, based on my understanding, so I think ontology should be the future in the systems engineering domain. And what we are doing in our community, it will be contribute more for the systems engineering community. So I will have a short introduction about today's agenda. So as you already have the agenda here in your hand. So so later we will have 4 presenters later, and also we will have a panel discussion. Okay. So yeah. Okay. Thank you. Thank you.
Can we maybe turn the light off for better visibility of the screen?
Yeah.
We try that?
Entrance maybe?
Are you sure? Let's try.
Yeah.
You can't see it.
It's easier.
Okay.
On the eye.
Yeah.
Good idea.
Okay. So any questions? So everything's good online. Okay. So maybe let's leave more time for the presentation. Okay. So okay. This one. This one?
Yeah.
Yeah. This one. Okay, so I need to confirm. Okay, good. So everything can see the screen, right?
Yes, we can see. Thank you.
Yes, we can see.
Okay. Well, I'm Alejandro Salado. I'm from the University of Arizona, an associate professor. This is a new community for me. So I'm not an ontologist. I love the idea of ontologies, but my work is really in systems engineering. I used to be a practitioner for 10 years or so, and then I moved into academia. So I'm not bringing any ontology for you today. I'm bringing a concern. Okay, that's what I'm trying to bring here, with the hope that I can lure you into our domain and we can fix it. Okay. So as Jinsi was saying, ontologies are coming to systems engineering. We have a few. You start to see papers that discuss about ontologies. You start to see people using the term ontology. You start to have people fighting along the lines of what is an ontology, okay? What is a metamodel scheme ontology, blah, 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 blah. I've seen papers with very sophisticated data-driven ontologies. I remember one, they took the ISO standard for systems engineering and they tried to codify everything into what objects we have with relationships like that crazy taxonomy there. We have some papers that do much smaller things, but I believe that all of them fall short on something, which is semantics at minimum. And I'm gonna try to talk a little bit about that. My focus is gonna be on the problem domain, requirements and all that stuff, because I think that's where most of the misunderstanding and misuses happen, okay? I will not try to be very rigorous in the use of the term ontology. So be nice to me, but I'm happy to learn more about that, okay? I know, I see. Yeah, I know. He was like, okay, not paying attention. Right? Okay. But I will certainly say what I think is important for an ontology. Okay. Okay, so let me see, I don't have a clicker. So now this is a meta model or a schema, SysML, some paper I took, and you can see that regardless of which one you look at, you're gonna see objects called requirements, you're gonna see objects called use cases. Most of them have this. Again, this is SysML based. You have Strata. I think this is the oldest attempt in systems engineering in the 90s, actually, before SysML existed. And again, you can see requirements, you can see use cases, relationships between them and so forth. And this allows us to do certain things. And Jinsi was talking about MBSE, right? So this is the birth of MBSE. That was the purpose. And you can now allocate objects in a model and tag them. And you can say, well, this object is a requirement. And we can find relationships between the requirements and do automated things with that. It is fantastic. We go even beyond these text objects now with SysML2, and they say, you know what? You can actually flag anything you want as a requirement. Okay, you can take a model, and any model can become a requirement. And again, we're working in foreign formulations, right? And this is the problem I have. So now you see lots of papers on this. You see OMG, SysML version 2 again, all these working groups, committees doing this and saying, yeah, you can flag everything as a requirement. That's awesome. We can work with it. I don't know if later today we're going to see those examples. And this is my concern. None of those efforts attempt to define what those things are. So yes, we have a class for those things, but what is the meaning of a requirement? We had a discussion yesterday, right, Chris, on the use cases and what do we mean by that and what is the architecture. Even the word interface, you'd be surprised. You can hardly find two people that tell you the same definition for that. And we're talking about basic stuff, right? We all work with interfaces. You go to any project, any engineering project, and they will tell you, for sure, I know what an interface is. I work with interfaces. I have many pretty diagrams with red lines and green lines and things like that, okay? However, again, we do not have common agreed upon definitions. Not only that, many of the definitions we have do not pass any test that you would do about meaning. You even have people that propose definitions, and when they use them wrongly. And they were the first one actually coming up with the definition, okay? So what do we have really in systems engineering with, again, I'm making now a leap of faith, I think, with all the ontologies, at least all the ones I've seen, okay? All the MBSE frameworks I've seen, we have something like this. They tell you, you have a class of objects called birds and some worms and relationship. And they start to put things there. So sometimes you're lucky and you actually have a bird and a worm, but sometimes you have, and then you can do some reasoning. It's a worm, but this is more or less what you actually find. Yes, you have things tagged as requirements and you have things classified as worms, but one thing is actually an elephant and this, and then, you get, this is a bird eating a worm. Okay, that's what we have. This is the state of practice. This is the state of the art. And I would be really happy to be proven wrong. This is what I've seen in every single paper I've read, every single implementation. Fantastic networks, as Cindy was showing before. Crazy networks, no control, no care about what's inside of those things and how we treat data. Now, this is really problematic, and I've got a few examples, but I'm going to show one that, to me, it's really interesting. It has to do with meaning. So, anyone familiar with the state machines here? Anyone not familiar? Okay, so this is a pretty simple one. This is actually, I took this from a training in SysML. Okay, I didn't come up with it. It's a state machine of a car, right? You're in idle, you accelerate, you get into cruise, and you can brake and all that. And we did a very small experiment. We took experts in SysML, okay? Not novices, we took experts, and we asked them the following question. If you are in braking state, how does the car react when you release brake and speed is 0 at the same time? Okay, very simple question, very simple state machine. If you work in real life, I tell you your system don't have that state machine, it's way more complicated. Very simple one.
You're
And we gave them options.
You're missing information because you might have,
It's okay. It's okay. I think we have there. It is incomplete.
Yeah.
It's okay. We simply tell the experts, you tell me what option you choose. Well, guess what the answer was? A uniform distribution over all the options. Okay?
Really? You asked more than 3 people.
More than 3 people. We have several people. We had a uniform distribution. Because actually SysML doesn't tell you what the answer is. It doesn't have semantics on it. Yes, it has a schema and a meta model and those things, but it doesn't give you an answer. Now, the interesting thing, again, these are SysML experts, okay, not novices. They know their stuff. They have a completely different opinion on how the car reacts, and now we're using this to design systems, right? So I may be expert 1 designing this as a model of my problem, that my designer is interpreting that it has a different behavior, and my implementer is having a different opinion on what the behavior is. So maybe I design it such that it ignores it. The designer thinks that it is not an expected condition, and the implementer does something else. And then you've got a problem. Now, this is the stupidest example I could come up with. If I take something and go in real life, it's a really large and complex problem that nobody can really make sense of what the actual behavior is. There is no way you could find these things, okay? So we need a way of defining problems, but now I'm gonna get, again, not into systems engineering, so I think this applies to everything, but I'm focusing on problem modeling. How do we define a problem? And as I mentioned as I mentioned before, the current paradigm is you can tag everything as a requirement. This is the current way of thinking. This is SysML version 2. It's okay, you can just tag something and say that's a requirement. And I can do a test and I can show a very simple sequence diagram, and I guess you will understand that. And if I want to use as a requirement, my question is, does that mean that the system must consume that resource, or that the system may consume that resource? And some people say, oh, you have the optional construct, so you can actually model it like that. And then the question is, does it mean that the system may consume the resource, or that the system must have the option to consume the resource? Which is a different thing. It's a different problem altogether, right? But this is what we are tagging as a requirement. Now, what's your real requirement? We don't know. Now, why don't we know that? Because actually, if you look at systems theory and problem theory, system models are not problem models. And now we get into a new way of thinking things. So it's not about really requirements or anything like that. It's that if you look at all the modeling paradigms we have, they are about modeling the thing, modeling the system. And we're using that to somehow tell us what the problem is. But from a problem theory perspective, you can't do that because they are 2 different things. There's some things that are problem models and some things that are system models. So you need, well, so that's what I have here, right? So whatever sophisticated modeling language you're using and the ontology that you are imposing into your system modeling language, sorry, you go up for failure because they cannot model problems. It is just a hidden limitation, okay? So what do we need? And this is the call for action here. We need an ontology for the problem domain. We need to understand what a problem really is. How does it really relate to solutions, to systems, okay? And as part of that, we need a model language that is based on that ontology. And I'm saying first the ontology comes. I hope that you agree with that. And then the modeling language might come. But we do not have that, okay? We're just looking all the time at systems. How am I doing in time? At 10 minutes, okay, good. I think I'm gonna do fine. So I'm not gonna give the answers because we don't have it. I'm super interested in this. It is part of our research. But I'm gonna share just maybe 2 systems theoretic constructs that are important, okay? And bear with mine with the words, but hopefully that gives us a sense of where this might be going. And again, I want you to remember the terms requirements and needs and stakeholder requirements, user requirements, business requirements, 102 types of requirements that you can have. And we're going to try to think ontologically, hopefully, okay, from a systems, at least from a systems theory perspective, conceptual, can we really have so many types of requirements? Is it meaningful or not, and all that? And how do you come up with defining them? And again, what we're doing in my research group is trying to use systems theory and problem theory as a source for defining our ontology. We're not using what we see in our everyday aircraft design. Okay? Because we understand that all the artifacts in existing practice, and again, I was a practitioner, I used to design space systems, they're wrong, really. Most of the taxonomies, they're wrong. They are not thought through. They are done for convenience. We have this, let's standardize it and run. Okay, this is how they're done. And then you've got problems. So what do we see in systems theory? Well, we start with two basic concepts, an open system. And there might be a lot of people from software here, so I'm gonna change what I mean by open. I take the general systems theory meaning of openness, which is a system is something that processes an input into an output. Right? So the key thing of a system being open is you exchange items through your boundaries. You do anything like that?
No,
okay.
Just
Okay, so that's the meaning of an open system. Okay, you can conceive, and I'm not gonna get into a lecture here on a system is something that is or system that you assign, but I will say, you know, you can conceive a system as open if you assume that there is a transferring of elements to its boundary, and you can conceive things as a closed system in which there is no, so the collection of those two would be, you can consider as closed is nothing goes beyond its boundaries. Okay. And again, I'm saying conceive. Now, do they exist in real life? Maybe the universe, but I'm an engineer, so I don't care. I can approximate something as a closed system. Okay, that's the point. And when I understand that, I can start to think about how those two systems might relate in the way they work. And I'm gonna say that open systems execute functions because they have outputs. As I said, it's because of the definition, right? And a closed system because they do not have outputs. I can only define them on the basis of states or outcomes. Okay. And now this is how it happens. And I'm going to talk about problem formulation, so it's coming. I may have open systems that produce outputs, and they engage in some way, and you achieve an outcome, which is what those individual parts want to achieve. And then we can talk about capability, so forth. So this is the main idea. Okay. If I show you, if I write something on a paper, and I would say, what is the output of the paper plus the pen? There is no output to that. Now there is an output of the pen, which is injecting or providing some ink, okay, and that ink is accepted by the paper, and writing happens. That's the outcome. Okay. If I don't have a balloon here with me. I usually have it, but if I blow air in a balloon and the balloon inflates, there is no output to the engagement of the balloon and myself. There is an output for me, which is I blow air, and there is air coming out of my mouth. The balloon can intake that air, and the balloon inflates. But inflating is not an output of the balloon, it's a state. And then I may get tired because I've been inflating, and the balloon gets expanded, and that's the outcome. So the interesting thing is that in reality, you only need two types of problem spaces. Okay, you need one that defines what do I want the open system to do, and what do I want to achieve in the closed system. Okay, so again, this is just one thought to start. This is how we're starting with our problem domain. Getting into an ontology. We need an ontologist, by the way, so if you're interested, I'm really happy to talk to you. But this is how we begin. Again, systems theoretic investigation. We start from scratch thinking, well, if there are two types of systems, my problem may need to be solved by either one. I may have problems that an open system can solve, or I have problems that a closed system can solve. So by definition, I only have two types of problem spaces. Either I want to achieve outcomes or I want to achieve functions. I don't need any other definition for them. Okay, so that's one thing. And then the next one, and I finish. I'm going to be 2 minutes late. It's that the notion of system really is a conception of, it's a construct of the observer. Again, this is, I cannot go into the details of why. And that actually means, and none of the system modeling languages can do this, maybe OPM only. But actually, there are situations if you really want to define your problems correctly, in which your system may be conceived as a system that transforms inputs into outputs, but it can be conceived as an input or output itself. And actually, from a systems engineering practitioner perspective, both are absolutely critical. So I don't know if you're working with ontologies for systems engineering, but you will see requirements to the process of developing the system, requirements for the system itself. Well, this is how we break it apart, because a system, and you can see it here, okay, it can be, again, something that executes a function, but it can be an output itself between companies that they are getting money and transforming materials into something that exists. Okay, so I just leave it there. There are many more, but two main theoretical foundations that I think are important to design the ontology, right? One is which kinds of problems you may have, desired outcomes or desired desired functions. The other one is system is a construct of the observer, and a given object may be conceived as a system or as an input-output in the same development project. Okay, that's the interesting thing. And with that, I'll just finish again with the call for action. Okay, problem models are not system models and vice versa. And we need an ontology, I think, desperately if we really want to make good use of what we're defining. And with that, I'm done. Thank you.
So, any question? Okay.
Yeah.
I really liked it. The thing that I'm intrigued. I really am intrigued. I can understand some of the stuff you're saying, but are the objects in your system models the same objects in the problem models? I can't grasp the distinction between the two. Or maybe it's because I'm not so close to system modeling. But it seems to me, I know this idea of conceptual systems, and I know people, I work with people who do systems modeling and stuff like that. And they seem to have these, I regard them as a mental problem about trying to work out what a system is. I can only think instructive, but is it just merely the choice of you choose, if you choose, you cut out a different perspective to do that?
So I think that's what we're coming at. They do not have the same objects. So a system may be a response to a problem, but the way in which you define a problem may not be related to the objects of the way you design it.
Have you got an example? Because I think in the end, it's the same word. I mean, if you take the universe as a system, it's going to have the same objects in it. So is it that the development is different from the system? Is it that?
And that's the question. That's the point, right? Again, we don't have an answer yet. But what it is clear is that it is a different thing. So you cannot take an object, which is a system, and call it a problem.
Okay.
That's the point.
But
That's the only point. You cannot.
Maybe we should take that out, but you making a claim is a different thing. I would, as a psychologist, ask you to tell me what you mean by thing, because I think that's the problem. Is that
Right. I mean, may not be a thing. Maybe something else. I don't know.
What else can be? Things are things.
Well, I don't remember, but relationships are things also. A type of thing. Okay. Yeah. If everything is a thing, then everything is a thing. But the thing is that, because, but the point is, as I said, a system is a mental construct. Okay.
I disagree with it.
Well, we can talk about that. I can show you in the context of designing systems, if it is not a subjective construct assigned to something, okay. And the thing is that thing is fluid. So
I know how to cash it out. I mean, that's probably
we can talk later.
We
can talk later. But the thing is, given one thing, you cannot assign it I don't say it not as a property. You cannot conceive them as both a system and a problem at the same time.
That's the thing that I don't understand. I'm not.
Okay, we can talk about that then. Yeah, we can talk about that.
I want to work out.
And it might be because of the meaning of what a system is. Because you think it exists. I don't think it exists.
You need to talk about what it means.
Sorry?
Could you define quickly what's the system and what's the problem?
So, okay, so you. Okay. So the main thing.
It's more interesting my talk for sure.
Right. So no, it's interesting. So let me see, close and open. So a system. Oh my, ontologist. No, okay. So I'm trying. Right. A system is something. It's something that either executes a function, okay, or achieves an outcome. Okay. Whereas a problem is a desired outcome. So it could be a transition of one outcome to another. It's a desired transition from one state to another one, and that's different. The word desire is what makes it different. Okay. And I don't know how to codify that, but it actually makes it different. And we can talk about that.
But we can talk about it.
Yeah. Okay.
Okay.
So thank you.
Maybe they have time.
We can talk about that.
Yeah. Like how does it say in the
It's a
final?
close connection to ontology. Figure out the right way.
Yes, I understand.
Okay. So Chris, it's your presentation.
My text was
Very interesting discussion. We have time in the panel. So
I'm talking.
this one.
Yes.
Okay.
Looks like mine.
Okay.
So I've done some work. Actually, I don't know where it is. I think we started pre-COVID because I seem to remember meeting people in person. So that means it must be pre-COVID. Is that 2 years ago? 3? I don't know. No, you're not. What? Well, okay. So I started work on sort of digital twin work for the UK, which is sort of a largish digital twin, and we're really trying to look at something that we assumed that would be needed to last decades. So it was large scale, if you like, I don't know, spatially, but maybe an amount of data, and large scale. We assumed that it was large scale in time because it's needed something to last for a while if you're going to make a massive investment in these kind of things. And I think people who work on asset projects are used to investments in something that will last 20 or 30 years. It's if you like, they're used to that way of thinking. I'm more used to software projects where you just think you have to develop it and the poor idiots have to run it. So it's like a year or 2 years. And it's not my problem. So it was interesting to move to this. How do I just press the button and it'll go? Let's live in hope. No. Do I press this? Sorry, I'm this one. No?
Maybe change it to the.
Yes, you are not in the. Here we go.
Yeah. Okay. Cool. This is going to build. This is boring. Okay. So these are the two papers. If you search for the National Digital Twin, they realised after a while that calling in the UK the National Digital Twin was a little bit UK centric. That's a UK National Digital Twin. These are two important papers. It was a large project, and you need to have this kind of bureaucracy surrounding it. It's worth looking at. I think it actually builds a bit more. So yeah, there we go. So they had a definition of a digital twin. They wanted to be as wide as possible. I know there are arguments about is this or is it a digital twin or whatever. I don't think that's the issue. I think it's large scaling sharing of data is the issue across a number of organizations or even within an organization. And let me just see what. Again, I think for those of you that came to my talk yesterday, they've got this talk about common languages. So they've read this stuff about maturity levels and semantic maturity needs a common model, and they were going down that path. The first stage was, in a sensible first stage, look at what's out there. You don't want to reinvent the wheel. You don't want to do work that you don't need to do. And I was closely involved in this. I don't always like my work. There's all sorts of things that I would like to change about this, but I think it's the I hoped that there would be earlier surveys. There was there's a woman in South Africa, had a PhD student who did a review, but I think she was more an IT and a philosophy background, and they didn't go the depth. And the other problem that I had is that I have I don't know, with mental disease, I have a desire for symmetry and structure, and there wasn't really a good structure behind a framework for analyzing these. And so we came up. I mean, it's not a perfect structure. That the 37 ontologies, there's 31. Oh, there's a paper you can download. I think the link's here. But if you search for it, I think Google knows where it is. I wonder whether I have. I don't know whether I thought I didn't have enough time. So it's okay. Okay. So I tried to come up with a notion of there being horizontal and vertical choices, and there's a notion of stratification or unification. And I think it's, if you like, I was trying to, probably with my prejudices, guess what the decision makers behind at least some of the ontologies were. And there's this idea of you unify things or you stratify things. And my ontology, the Bohr ontology, and the people who work in sort of the 4D world tend to be unified. If you go back to Quine and if you're a philosopher, there's someone nodding at the back, the sort of the mid-20th, well, let's say a bit later, say the 60s onwards, maybe the 70s onwards, till the tail end of till 1990, the broad mainstream was a sort of, you can see it as an attempt to understand science, and it was a unifying attempt to simplify. And then since then, I think BFO is an example of sort of a trend of neo-Aristotelian, with the pendulum swinging the other way of trying to stratify. In fact, I had some pictures in the early one, and I actually might didn't have enough time. But if you go to the paper, and you can find some presentations I made this, you will see that the BFO is maximally stratified. If there's anything to stratify, Barry will do it. You know, he stratifies all over the place, and you can have an argument about the benefits of, and that's not really what I'm trying to do in this paper. I'm just trying to give you a roadmap of what things are out there, and if you like, where they sit. And so there's a series of, this is just one of the slides, this series of slides, and I think this again talks about unification and stratification. And there's something else that's noticed in the literature about this is that it's a hot or cold thing. I mean, in English we say it's a Marmite thing. That probably means nothing to most people here, but you either like it or you don't like it. It's saying you either want to unify or you want to stratify. There's something a bit weird about BFO in terms of at least one of the stratifications. He's got 3D and 4D in it, and there's an interesting picture in the survey where it shows the amount of links that he has to make for locations. There's someone I was talking to at breakfast, I think, about the choice between 3D, and if you've got them both, the complications that arise because you have to have locate the different positions. And there's quite a lot of literature. I mean, people get really interested. I can point to the philosophical literature. I'm not sure there's literature anywhere else. It's only philosophers who are interested in these kind of things. There was something else. I'll go back. I don't know whether we can see it here. There's quite an interesting set of choices here, which I would, if you are going to choose on top ontology, if you are going to do modeling, one of the things I think you need to do is look at the kind of constraints you build in. I'm trying to remember, I think BFO doesn't have multi-levels or multi-level types. I think it doesn't have first order relations. It does actually do something which I think is really good. We'll come on to a second. It does reifier instantiation. So there are these ground level choices, right at the bottom that most people don't have any idea about, that actually have a massive impact on when you do your models, what happens. And I think that's going to be, that's the kind of discussion I'd like to have with you. So, because I think most people come to this idea as this, I have adequate resources to deal with this. I know how to deal with it. But I think when you're dealing with a new set of problems, which I think we're dealing with, we don't actually have the right we don't even know what the right intellectual resources are. So it's a problem in your terminology, not a system. And so it's good to try. I would go through these labels and make sure that you know roughly what they mean. I don't think they're not difficult in the sense of being extraordinarily complex. I think they might be difficult because they're unfamiliar. And I think unfamiliarity is probably more of a barrier than difficulty for these kinds of things. Okay, I don't know how I'm doing for time. Well, I don't know. Okay, so it's this from a management perspective. When they were doing the digital twin, they divided it into these 7 circles. I mean, 7's a good number. Circles are good things to have. It was just a way of organizing. And at the bottom, you have the, if you like, the more data or modeling focused things. And then the bit that I was particularly interested in is you have these 3 levels. And the idea, I'll talk about the core construction, and that's, if you like, the nature of the building blocks. The top level ontology was the way in which you structure it, and then the foundation data model are probably more high level patterns for dealing with things. I said anything I want to say. Yeah. Okay. And again, I have there's a longer side. If you look through if you search through these slides, the presentations here. This is a gross simplification, but I would argue a useful gross simplification. I mean, with this stuff, it's horrendously interconnected. Okay, so the other thing is that it's quite useful to have a focus, not a requirement, because I don't like requirements. Have a focus. So one of the things we're trying to say is that, look, what problem do we want to solve? And I think there's something that David Leon mentioned, is that across this range of standards, there's a range of geometries and topologies, and they aren't when you try at ground level, when you try and merge the data, you get these awkward things that turn up. And I mean, they're practical problems that turn up. And it turns out, because we've done work in the past, or I've done work in the past, is that you need to go back to quite a deep level to find out what's going on about these, and to try and find a common way of talking about them. So that what's happened is that there's probably, you can think about it as a component level, there are probably these 15 or 20 different components which you can configure in different ways, and they configured them in different ways for this stuff. And then when you try and work out how to get together, if you don't know the components, you can't work out the mapping. It's like if you think of, probably haven't got time. Okay. So This is if you remember, let me go back. Is this going to work? If this is this level here, the core construction ontology, and I'd like to spend a little time on it. And please interrupt if you don't understand or if I'm not explaining very well, which is there's a more than 50-50 chance that will be the case. So the thing we did work with a series of people. Salvatore and Oysten did most of the work of the actual formalization. There's a predicate logical formalization based on pluralities. I can explain why we used it. It's inspired by work of Kit Fine in terms of the way he does constructors. We call it everything's onology. It's good. Apparently, it's good marketing. Maybe it is, but at least it's recognizable. So we have a constructionology, and what Kit, the insight that Kit had is he claimed that there's a whole series of things of the relations that you think about the world and the way the world is grounded that we think are different. We say problems are different from systems. Okay, I'm joking. Yeah, I'm joking. But we say types are different from instances, and mereology is different from set theory. And what he realized is that he says there's actually a plurality of different kinds of parts. And if you look at the way in which they're constructed, you can reconstruct it. So what we have built in various different ways, and there are some papers. I've got some papers from I think the 2019 and 2020 that if this does interest you, if I've managed to inspire interest, I can point you to, is that you have this general pattern of construction, and you can construct sets or types or whatever. You can construct individuals and their mereology, and then you can construct relations. So there's a single way of constructing things, and there's also something else that the neo-Aristotelians like to say is they moan about Quine and Lewis having this desert landscape and a single flat structure with no connections. So they say these things are connected, they're grounded. What's interesting about this is this gives you a grounding, a way of grounding things. So the example that Kit uses a lot, which probably is a little bit too academic for you, but you can translate it. He says that what's interesting, if you take the Aristotle and the singleton set of Aristotle, it's plain that the singleton set, let's say you take a pump number one and the set of singleton pump number one, the set seems to be somehow further on down. There seems to be a dependency relation between these two. And that's what we're able to do here. And also there seems to be in relations, there seems to be the relations seem to be dependent on the relator in some way. And again, this cashes out on this. You're going to tell me I've only got 2 minutes left. Okay. So you've got what you've got here is you've got I claim, yeah, and I'd love to be challenged. If I'm wrong, I'd like to know sooner rather than later, that you've got a really, really simple structure at the core that's actually functionally richer than I would claim, than most of the modeling systems that you're working with now. And there are instances I can show you in different ways in which you've got built constraints into your things that this doesn't have built. Yeah? And if you read the top level survey, you'll see some of those cases. This is a work in progress about how you get up to 4D space-time. There is just one thing I mentioned, is that at the core of this is world lines, and I don't imagine you have, but in previous presentations I'll go through the detail. I point out that ontologies have been around for quite a while. There were, I think it's the Aufbau is 1928. I'm looking around. Is anyone going to disagree? It sound about right. Anyway, so 1928, Carnap came up. There were actually two ontologies you had in there based around world lines. I think there was Einstein's and Minkowski's work on space-time and physics drew an enormous amount of admiration. People built on that. There's an English biologist, Woodruff, who was working with Tarski. I think it's in the late 30s, 37, 39. I'm getting a nod, good. So my memory's working, despite the lack of sleep last night. Where they talk about, but it's all starting with world lines, and there are other things. I've got a whole series of references you can go to, and in fact, if you go to in physics, if you go to Hawking's and Penrose's work in the 70s, you get the same. It's if you like, even though it might seem that the things that I'm talking about are radical and if you like, not mainline, world lines are and were mainline in terms of the ways of doing things. And if you go world lines, you go something called 4D, and you probably haven't got time to talk about the difference between 3D and 4D, but it's a natural progression. And 4D is we talked earlier about stratification and unification. 4D is a way of unifying space and time, a unified way of talking about space and time. So this is suggests that a unified strategy is a good way to go. Ah, okay, good. I've done this in time.
So question?
Is that a good sign or a bad sign?
Yeah. So may I ask one question?
Of course,
So you
yes.
mentioned the 4D work.
Yes, yes.
So can you explain about some detail about the 4D work? So D is dimension.
Okay, so yes. So there's a simple level. If you're trying to think about our actual world and most things, there's a difference between the idea is you have a series of time shots. There's now, and there's now, and then there's now, and then you relate them by having some kind of relation between the snapshots. The 4D says no. Standard classical Einstein physics or Windhouse physics, you have 4D space-time. There are different kinds of 4D space-time. Actually, when you push really hard on it, particularly if you have a way of dealing with modality called possible worlds, I'll explain that if anyone asks, but you could actually end up with, there's a Abbott, you want to know Abbott, that land? Okay. There's a famous book about different kinds of worlds, or the 1D world, 2D world, or 3D world. I think it's from 1880 or something. So there could be other possible worlds with different dimensions. What it turns out is 4D hashes out to a view on Mereology. So you can have identity as if you have the same parts, you're the same thing. So 4D is a particular expression of this underlying principle of identity. And the way I was explaining it, maybe do I have a minute to explain?
Yeah.
Okay. We haven't got things to write on the board. So I was involved in a project with the Ministry of Defence, where we were looking at something called air traffic control. One of the things that's quite interesting is that there's a certain way of thinking about 3D that we end up with certain things. So if you were in your 3D world, fine. What they did is they marked out a bit of space here. They mark it out for a period of time. So you get these square blocks like this. And I was doing it with a guy who was an expert on these air traffic controllers, knew nothing about ontology, thought couldn't understand we've got any practical purpose whatsoever. And I went through this thing. We were explaining how you do the next thing. What we're saying is, well, actually, okay, so therefore, if you've got an aircraft, if the aircraft goes like this, but what you could do is the aircraft just flies down. So if you like, you think of the space of the aircraft going up. But you can only do this in 3D, just without thinking of assumptions. And anyway, this guy we're working with went out to see his friends at the evening or a beer in a pub, and he was saying, "I have these idiots. They're doing this really stupid. Why are they wasting our money on it?" And I said to him, this is about when there was a war in Bosnia. The Americans flew from the summit. I don't know. I can't remember the name now. They flew from the Pacific base all the way to Bosnia and they were trying to do sorry, bombing these. Sorry, my European history is not my strength. But what they first did is they first decided that they were going to have 3D. They were going to have this corridor that went all the way from the Pacific to Yugoslavia. What they realized is that they then have to cancel all flights over the Mediterranean. I think it was in the middle of summer holidays for 18 hours. And they said, this is politically not right. So what they did is they then had to go to this thing where it doubled the length of time, because every time you did it, you've got to add a margin for error. These things apparently ended up going off. And they also had a big thing there were some hills that were safe in near Bosnia, where they circled there for 2 hours because there was a whole lot of safety things they'd done. And if they'd done this, they wouldn't have had to do it. There was another story about they were trying to bomb Saddam Hussein and special forces who worked out in this restaurant, and because they had to do this, it was an extra 2 or 3 hours added to the operation. Maybe this is boring stuff, in terms of shooting and things like that. So I apologize if it might be offensive. But it does sort of illustrate the, if you like, that there are practical implications to what is going on. And what's intriguing for me is that you can see when you look at the data, the embedded 3D view, and this 4D view, bring out its flexibility shapes in space. There's another thing to do with replaceable parts. Looking at the data, you know, right?
Maybe we can have some time to discuss later.
Okay.
Okay?
Yep.
So, thank you. So next presenter is Professor Yu Ming from Tsinghua University, which is that's an engineering,
Online.
that's a university, not the only engineering, that's a university in China. So, okay.
I'm ready. Can you hear me?
Yeah, we can hear. So,
I
are
will
you
share
sharing?
my screen.
Yeah. So,
I just open my camera. Hello.
okay, so, okay, yeah. Have you sharing your presentation, Professor?
I
Yu?
try, but no result. I click the button beside the microphone, but
Okay.
maybe you should give me right?
Authority, right?
Yeah, also ready.
Yeah, okay. You can share. Otherwise, you can send and we share. Okay, so maybe Professor Yu, you can send me, maybe you can send
My presentation to you.
yeah, maybe to the WeChat,
Okay, I try.
you can send the presentation to Zheng Yu. So
Wait a moment.
yeah.
Okay. Wait a moment. Okay, I send it to WeChat. Can you find it?
Yes. It
To
can
the
work.
group.
So you can. Yeah, I will copy it in the present in the computer. Okay.
Can I operate the slide by myself, or I need
Yeah,
your assistance?
I can help you to. I can help you to control your presentation. So
Okay,
when you
thanks.
want to go to next slide.
Okay, thanks. But I need to
So,
how to say click some.
yeah.
Not come out yet.
Okay.
我那个
Okay,
PPT
good.
里头有很多跳转。
So as we know, we already have researcher from US. Okay. So
Okay, can I start?
if you want to do something, let me know. Okay.
Okay, thanks. Firstly, good afternoon, good morning. Okay, because my network is not so good, so I would not, I would hide my picture so the sound quality could be okay. Is that okay?
It's okay. It's okay.
I close my camera. Okay, yeah. Okay, today I would talking about a very simple topic just called modeling, ontology, and the system. And my view and the conclusion may be also very simple, but I think it is very important, especially for me, because we understand some very foundation problem. So this will give us a clear direction for our futures research. Okay, next slide, please. Okay, I will talking about first about the research background. Could you click the research background? Click
Oh, okay.
research background. It's linking.
Yeah. Okay.
Yeah. Thanks. Go. Okay, currently we do research on MBSE, just like everyone do here, especially for cyber physical systems, digital twins, IoT, such kind of very hot topics. And we wanted to do a system modeling for these systems, but we want to use very simple, very, how to say, advanced tools. So these tools need help us to build the models both for cyber and the physical world. Now, currently modeling works especially for physical world, but we need to combine them together. So this is the background. Okay, again.
Okay.
Return. Yeah.
Ah.
So our question is how to build an ontology model for various models within MBSE. That's the problem facing for us. Okay. Button. Return. Yeah. Click the back
Okay.
button. Sorry, I have much more. Yeah. So before we give my view, just to have a very quick view about the system, definition about the system, definition about ontology, and the definition about modeling. Okay, system, please. So this is the definition from ISO standard. We know a system is a system composed of a set of interacting system elements. Okay, button, please. Yeah, so I would not repeat this definition, but the conclusion is in the system, the elements and the relation are the two key issues for system description, or we call the modeling. Okay, please return, we go back. Okay, now about ontology definition, please. Okay, so this definition comes from BFO. So ontology model is a representational artifact which comprising a taxonomy as a proper part, whose representation are intended to designate some combination of universals, defined classes, and certain relations. Here, the universal means the classes and the certain. We think these two are very basic and fundamental for ontology modeling. Yeah, please go back. So modeling again. Okay, this is the come from the MOF, the layer, just like shown by Jinzhi in previous presentation. There's four layers. Okay, I know everybody see this again. My conclusion is for any kind of model, no matter it is a model, a meta model, a meta model, no matter what model it is, each model has its own meta model. That means every model has a description to itself. This is the conclusion. Okay, go back. Yeah, with these three definitions, we found our findings and the concept. Go, please. The first one is any model should have a description, just like a meta model. Okay, again. And an ontology model can be built for anything, including models and the meta models. So therefore, again, please. Therefore, we think a meta model equal ontology model, or maybe we can say they have the similar function to explain something or explain the model itself. Okay, again, please. Therefore, the second finding is for any model, including the meta model and ontology model, etc., is comprised of a set of basic elements. And these basic elements are we call the building blocks, which can be used to shape our real world, our models. So this is quite similar to the definition of systems. That means we need to find some basic element and relation something. So that means when we build a model, actually very similar, we wanted to build a system. So the conclusion is, so to build an ontology model is just like to build a representation system which confirms to ontology paradigm. That means the ontology model just like other model systems, but it should follow the ontology paradigm. Okay, please go back.
So do I need to link?
Okay, you can click it. So this what is ontology paradigm? So that means just three. First one is taxonomy and the relation and attribute and the terminology. We will not go very clear. We go back. Sorry. Yeah, we go back. Yeah, too much. Yeah. So yeah, go back. So the conclusion is also very simple and clearly. The first one is the methodology for any kind of modeling is the same. Is to find or define the basic elements and relations. This is the first one. The second one is for ontology modeling. We think the key issue is to finding and define the building blocks, but in taxonomy way, linking them with the top ontologies such as BFO, Bolo, CISO, etc. That means we wanted to building our domain ontology. We should find these building blocks, but linked with the top level ontology model. And finally, the following the ontology paradigm is very varies of attributes in both static and dynamic. So this is a very simple conclusion. I just very interesting about before Chris's the four dimension space and the time, but I don't know very much, no much, but I think all the attributes should be time related, space related, and also this lead to, we say, the static behavior and the dynamic behavior. So this is our research and very simple, but I think it's the important conclusion. Thanks.
Okay. Okay, thank you, Professor Yu. So, any questions? So maybe may I ask one question, Professor Yu? So as I know, you already have some research in your group in China now. So how's ontology work in China? Because I think a lot of people, they are very interested how the ontology work right now in China, how this ontology can support the industry work. So could you have some comment on this?
I think in China, we're still in the very initial stage for ontology. At this moment, we have not seen any report about some industrial ontology or domain ontology. Maybe we are in the pioneer to do this kind of research in China.
Okay, so that means maybe we will have a very good chance to collaborate in the future in China. Okay. Okay.
Yes, I hope. Yes, I hope.
Yeah. So thanks, Professor Yu. So maybe I will introduce the next presentation. Okay. So Professor.
Thanks all. Yeah. Bye bye.
Okay. So let's continue our presentation. Next presentation is presenter is Rebecca from Airbus and Xiaochen Zheng, Dr. Xiaochen Zheng from EPFL. So everything is fine. Okay, everything is fine online, right? Yeah, good. Okay, so Xiaochen, you can your presentation right now. Good. You want me to help you to click? Okay.
Yeah, I mean, before formally starting, I just want to say a few words because during the past few days we have been talking a lot about ontology and terminology, system modeling, mainly focusing on the theoretical part. And I mean, many speakers also mentioned that it's not easy. Also, it's kind of not so frequently to see some industrial applications. And during our previous project, we have been trying to explore the ontology, the application of ontology in some industrial cases like in the Airbus, like to how to support the knowledge management and how to support the knowledge reuse. So yeah, I mean, it's kind of different from the previous presentations. I hope we can provide some new insights. And so yeah, with more delay, I will give the floor to my colleague Rebecca. She will introduce the background of the pilot, then we will go to some technical points.
Industrial ontologist and knowledge management expert in Airbus. So what we will present, so first is Quality Airbus pilot in a nutshell. So Quality is a European project that we have worked and collaborated with EPFL, Fraunhofer, and Visual Components for the last 3 years. And the project just ended last July. And these are the results we're showing you today. So the objective of the pilot in this European project was to enable MBAC and a collaborative design process between the aircraft and the industrial system domain, overcoming three main problems of knowledge management, interoperability, and decision making. So that was the core thing that we wanted to demonstrate. We use an industrial use case, focus on a process, manufacturing process design. So it's the orbital joint process that we use in all of our programs. And with that, we built a trade space framework prototype that showed all ontology capabilities in order to fulfill these bottlenecks. So this is the functional architecture of the pilot. Okay. You can see in the front end we have two different users. So we had an engineer and an architect to differentiate the decision-making process and the MBSE, MDO processes. So we had a requirement management block first, an architecture definition block, in which we have different phases that we will explain. And we had a visualization block where we checked the co-simulation between two different types of models, 2D and 3D models, and the trade results that help the engineer make in the decision-making. So all of that was supported in the backend with a system integration block in which we used ontology-based engineering solutions. And that is the. Do we have something else? Yeah, regarding the toolchain, so we demonstrated this project with this toolchain, but we ensured that what we were demonstrating will be comparable to any other tool sets. But in this case, we used open source tools like OnRec, and other tools like Metagraph. We used some libraries, Python libraries for 2D models, and Visual Components that was a partner. We used his solution for 3D simulations. And on the system integration, we used the Neo4j capabilities in this case, but we had chosen another one, and a cloud server to enable the connectivity in the data. And so we, in order to manage all of that, we created an application ontology for the use case. That is what we will explain next. Linked to the IOF core, and
Yes, it's correct. Actually, as you can see here, we have also in the previous slides, we see the framework contains multiple functional blocks. So today we cannot show all the blocks since we are this system engineering session. We're mainly focusing on the back end, the system integration block, which is based on ontology and the knowledge graph. Then we talk about the interaction between the graph database and the architecture definition block. Basically, how do we transform the information stored in graph database to the system modeling tools. So to support that, previously, Jinji mentioned also there's this IBSE methodology. We have different layers from meta model to model to the real world. Then based on this methodology, actually, we use this GOPBRE methods, you can call it. Basically, it defines the basic elements to construct, call it meta model. And it's one part, let's call it, one part of the final application ontology. Here we show there are three on this layer. We see three parts together. We integrate them into the IOF core. We use it as a up-level ontology. We include these three separate ontologies into this IOF core framework. And so they represent the, on the very left is the domain knowledge, which is the mostly used or commonly being modeled apart. Basically, we define the classes and the individuals to describe what a real assembly process looks like in the reality. And IBSE ontology basically define the classes and also individuals relevant to the modeling part. Basically, that's the virtual space. And also we have another part is the requirement part is relatively smaller. It defines the elements to define a requirement, especially in the industrial environment. So here's the hierarchical methods we are following. Basically, to develop this MBS ontology, we basically map these 4 layers on the very left, from meta-meta model to meta model to the graph to describe the real world. We map them to the ontology world. Basically, we can map them as like class, object property, subclass, individual, and in the end we have an ontology. It's kind of one-to-one map. But of course, in reality, you will find some overlap. And sometimes the graph can always decompose a graph into a metagraph. A metagraph can further decompose. It depends. Let's go back to the previous discussion. How do we define the scope of the system? Now, here's the tool we used. Basically, here also I want to mention that we used the previous version of the IO core, which was released I think 2020 or early 2021. And now we have a new version, but we haven't updated yet. Basically, we insert all these classes in this framework and define some basic elements based on the GPI methodology, and then we use this to construct a model. And yeah, here is the overall, let's see, the workflow. Once we have the ontology ready, we use this ontology as a backbone to construct the graph database. And here we use Neo4j, like, because they provide a community-free version. And then we can trigger automatic generative algorithm. It's like a customized algorithm with some Python and some Cypher query language. It's a language provided by Neo4j. Basically, we integrate all these queries into this Python script to run all the queries and generate the new process automatically. And after this process, we will have the new alternatives for the future assembly process. Basically, in the ontology, what we have defined is about the current or the existing assembly processes. And now we are trying to reuse this knowledge to generate like a similar computer-driven process for a new model of the aircraft. Once these new solutions are generated, it can be exported because it's in a graph database in RDF or OWL format. And what this part system definition block does is try to here's the generated solution. Then we develop with this we can call it middleware or plugin, basically to transform the automatically generated processes into the OWL format file that can be recognized by the modeling tools. Here is where the application ontology works. Basically, if you remember in the previous slides, we were mentioning in the application ontology, we have the domain knowledge part and we have the MBSE part. So during this process, we are mapping the generated process from the real world to the virtual world. So that's all the elements or the individuals representing a real operation of a tool or machine in the real world is transformed to these MBSE models. It becomes the elements in the model. So then after that, the transformed OWL file can be imported to a system modeling tool like graph here we use. And then once it's imported into this MBS modeling tool, you can play with it based on the experience or based on the preference of the architects or the designer. They can, based on their preference, they can transform the process into different formats. There are many different choices, of course. Here we follow this MOLP methodology, widely used in Airbus. And then, of course, during this process, you can do second round check and optimization to reconfigure all the operations if necessary. And you will choose some of them based on his experience. To then export again, seal back to the U4G database, and finally the selected or reconfigured processes will be imported to the 2D 3D simulation blocks, and later will be presented to the final user to help them to make their final choice of the processes. So due to the time, we cannot go to details about the 2D 3D part, but here are some examples you can play with the generated processes in the method graph modeling tool. Of course, you can choose other tools. There are many competitors out there. And other type of models you can transform inside. This is just some example. Here I show a short video just to show from the end user's perspective how do they see, because first we have been seeing that it's not reasonable to show the end users all the ontology stuff. They are not familiar with that. We need to find a way to show them. So here the architects define the industrial requirements, and we used on-the-rack software to import. Then it can be, of course, you can modify and reconfigure all the any of these requirements, and then it's integrated into the graph database. Basically, here he's trying to reconfigure all the data, because the auto-rec has done is imported from some previous Word or Excel file, and then he triggered the automatic generation algorithm to generate all these new solutions, and then, as I said, it's transformed, imported into the modeling tool. Play with it and reconfigure and to optimize. And yeah, and there are different activity diagrams, etc. You can think and launch the 2D simulation. Basically, this is the discrete inline simulation. That's to calculate some KPI values, and then we can present the result to the simulation. Basically, here you can choose which indicator you want to compare. In the end, we will see which solution can satisfy the predefined requirements or not. And yeah. In the end, you can choose one or two of them and to simulate in the 3D software. This is part, the 3D simulation part is supported by the visual component. And yeah, from that part, just to mention shortly, they can also import the OWL file directly and map to their 3D modeling software. Yeah, 3D software can provide different views. You can view it on a computer, or you can use the VR device to see it more interactively. That's it. I'm not sure if Rebecca wants to.
Okay.
And for your information, maybe during the last time or during the coffee break, we have a video show in the coffee room, the overall story, basically the background and also advertisement for the afternoon session. We will have another presentation to talk about the automatic generative algorithm. How do we use ontology to automatically generate the solutions? We cannot include them here. It's another key part of this pilot.
So maybe the time is limited. Maybe one question. Okay.
Yeah.
Can you put your 14 slide? because you have derived the ontology from the DFO, and most of your concepts involve process. 14.
14.
Next one.
Okay, this one.
This one.
I need to go close to see because I think it's really small. Are your model also processing your model? You know, events and process? Because you have like activity, not here, but I see
Okay. Now I know which one you
maybe
mean.
in the wrong slide.
No, it's this one, I think.
Probably.
He's the web prodigy.
So
Yeah.
you have a current and you model activity has a current.
Yes.
A current is the process.
Okay, I
The
know.
process, in the process, under the current we have the process and the operation defined. And then basically, as you mentioned previously, that part was done during the domain knowledge part. That is the main, the most common.
Because you have some middle level ontology and the currents are more like a particular in your.
Yes, exactly. Because we reuse the IOP core and IOP core use the BFO. BFO is basically the current and current stuff.
Okay. And then how do you model the process? Because BFO is very generic about.
Yes, exactly. So the main part of the for us maybe different from some other others. From the very beginning, we know our end user and we know more or less the scope of the system, and we are not focusing on the whole complex assembly system. We're focused on this assembly process for the object joining. And we have some, I mean, the knowledge source or information source, mainly the well-documented information from previous assembly processes. And also we ran several rounds of experts interview, basically to ask their experience, because for them, they have some organized knowledge, help us to improve the ontology, let's say, make it more closer to the reality. It's not like something we invented. And then once that step is done, we started to make it like conform with the IO structure.
Okay, good.
Maybe just to mention one thing, because there were some questions regarding the use of IOF for what was the maturity or the completing that Airbus and this use case. So we've put on the table these use cases to check and demonstrate what we can take out of it and how it can benefit. So this is right now level at TRL5 of maturity. So we're assessing this as a research activity still, which is quite promising, but for now it's still research.
Thanks.
Impressive.
We are already paid for. So Alejandro. So how many chairs do you need? I can bring only 3 chairs is enough. Yeah. Okay. So maybe I will confer if Professor Yu is online. So.
大约6个小时出舱活动的全部既定任务。这次出舱活动当中，3名航天员分工明确，由航天员刘洋开展。
今日结束了吧？
这也是他们首次。
Professor Yu, maybe panel
is finished. Okay.
No, we have a no, Professor Yu. It's not finished. We will have a panel discussion here, and you will be one of the panelists to discuss about some question proposed by Alejandro. Okay.
Okay.
Okay. Okay. Yeah. Take a seat. So Xiaochen and Rebecca.
Let me move the camera so that we can see. Okay, so closer to the camera, please. Yeah.
Okay, I think we're to start. So welcome to the panel on ontologies and systems engineering. You know all the panelists already. They've introduced themselves in their talks. So hopefully you have lots of questions and make my job easy. Just sit here and indicate who's gonna ask a question. So does anyone have any question to start with?
Yeah, I have.
Okay.
But because you comment that this process and are already organized by Airbus, and I believe so, at least. Otherwise, I will stop flying with the trains, you know. I hope that they have a better organized. Why they move to use ontology? What's the benefit? Because it's already the worst part, which is the modeling itself, it's already done. Why using another modeling language and migrate to many sequence of modeling tools? That's the idea behind it.
Well, I can start. So there's different ones. So first, we want to go towards using semantic web technologies, our data length, and have it accessible. So in this specific process, you see that we have different steps. So we have a requirement definition, architecture definition, and multidisciplinary analysis and optimization. And we need to link all that processes. So to do that, using new languages and new technologies that can help us, reason in our data and do more than we're doing now. So we do need to do that.
So it's to provide the user a better integrated view over the process and the data.
So first is for interoperability, sure. So and it's for to have this data flow, continuous data flow, right? Digital continuity. And second, that what we presented here is to enable more like ontology-based engineering systems, where we can act on the knowledge that we have and reason on it, and create, so propose to the architect new design options that he cannot imagine. Because we're saying, okay, historically you have done it this way. We propose you already these options that you can think as an architect. So we are supporting this engineering process.
Just a short complimentary, behind that is also the, I think, demand from industry, not only Airbus, other similar companies, demand for more efficient knowledge management, knowledge reuse, and also to accelerate the design process. And we have been talking about knowledge management for many years, but in reality, do we really have a really efficient tool to help us do that, and especially how to reuse them? And in this case, ontology could be a good option. It's at least what I try to explore. And also, as Rebecca mentioned, it's quite important to support the interoperability and the stakeholders. I've been seeing that the architects, they are familiar with the MDSC and system modeling. If you ask them from the very beginning to link all the design is set to the industrial requirements, hundreds of them, maybe it's not that easy to handle. We have this kind of tool that can integrate both modeling section and the requirement definition section. That would be a plus. Yeah.
Can I say one comment on this? So I think in addition to what you say, which is interoperability and common model background, which is a most technical aspect, I think through the process to create this ontology requires an agreement among various stakeholders, create a common vocabulary with, let's say, agreed definitions, the terms used. And I believe that this helps to enable or to develop trust among these stakeholders. So even inside the company, or if you extend this system to your suppliers in the value chain, I strongly believe that this working with agreed ontology models will help to increase the trust of data sharing. So why you want to extend this to your suppliers? Because you want to share data with them. So having a common language helps to develop trust. Not only, so we do that because we talk together at the human personal level. So if this is enabled also by software system, this will increase this level of trust, which is required to share data. So ontologies are trust enablers, I believe.
I have some curiosity. Why you are using O in the middle of this process? You have a or
So O is only one of the options. For example, IOF, the core, the IOF core, it supports several formats. Officially in GitHub, I remember it's Turtle. To create ontology, there's no big difference. But finally, in the end, it will be RDF in the graph database. So here we use OWL. It's only because our partners, they are more familiar to OWL. For example, the 3D simulation, their part, the OWL is more convenient for that. But yes, in the end, I mean, it's the RDF. So we can, yeah.
Any other question? Okay, so last one, also for Professor Yu. How do you show value of this? Your company, your sponsors. How do you show value of the ontology of systems engineering such that you get the funding for implementing it?
I don't know if
Professor Yu, do you want to start?
Yeah. Can you hear me?
Yes.
Sorry, could you repeat the question?
So, yeah, absolutely. So the question is, how do you show that developing an ontology for systems engineering has value? How do you
developing
prove that?
the value?
It is valuable.
It's valuable.
Benefit. That it provides benefits.
Yes. I think in terms of knowledge management, I think ontology could play important to share the knowledge, share the concepts and experience in a specific domain. I think this is quite useful and valuable.
Okay,
Is that okay?
Yeah, sure.
Yeah, this is my opinion. So I think for actually in any kind of system building, we call system engineering, the first things is to give very clear definition for any core concept and idea within this system. So I think the ontology will play a very important role in this issue. This is my idea.
So I guess, if demonstrating value of systems engineering is already difficult in many contexts, I guess my point is if I want to champion this in my organization, what your recommendations would be? If I want to tell my organization, I think we should bring this to our systems engineering processes and way of working, what would you tell?
Maybe I can comment. Well, we say some words about the business value already, right? So we want to make our design process shorter. So, we have always the business value drivers of, we want to make it less cost, more quickly. But now we have more and more things that bring value, not just for the company, but for the ecosystem. So we need to check that is environmentally sustainable, that it complies with different things, which brings more complexity still to a complex system. So that it's what we're these type of solutions that we bring to the people that need to make the decisions in our process. So these industrial architects, industrial systems engineers, they see the use of it, okay, when they can take decisions.
You can ask them. Because I have old ontology being used by industry, and it's interesting how fast the time, how many different uses you can have for this defined vocabulary. For example, now Petrobras are facing what they call the mountain of data. They have plenty of reports, tables, images, and data from several providers and so on. They know that they have the information in the data, but they have no idea where is it, whom is this information. So we have defined it, of course, in different levels of granularity. We have some ontology, very detailed, some other are more general. But we use this for a system that we developed together. That's a kind of internal Google. So we have this, we scan the database with some S, but we scan the database, the document base, and we index this information using this vocabulary, which is not complete, which is not the same level and so on, but it's something that they use in daily basis, And then we also index pictures. It's a large problem in exploration. Using geology, they use a lot of maps and pictures and so on. And we use also to index the pictures, and then they go to a kind of Google search, composing search, and they find the source of the document. Great. And it's several different ontologies developed through the caves, and they are put together now, sometimes adding some new vocabulary. Of course, that needs a group that is auditoring the ontology, but it's very useful. Very good. So producing automatic reports, it's plenty of different things that we are doing now to help in developing machine learning and putting some knowledge in machine learning with algorithms. Plenty of opportunity to have something like. So use your imagination.
And follow that point. I actually mentioned Google. Actually, many industry companies, they kind of been trying to do the realize smart manufacturing and smart maintenance, etc. And they have huge amount of data, as you said, in their databases, structured databases, whatever. They have well-structured management about the data, but sometimes still you need to do some very specific search to find the relevant data. And they want something like Google, very simple and very efficient interface. And to do that, because Google is doing use their own knowledge graph, which is proposed by Google. But in industry, when you want to build a knowledge graph, because you have two ways, like Google, you have all the big amount of data already available and online. But for many traditional manufacturing or other industries, that's not the reality. You need to find a way to organize and to link all this data. And ontology could be one of the good solutions. Because once we have the ontology to link, to define all the terminology and to link all the database, and then we can use ontology to create the knowledge graph. And it's a very simple example of one of our master project is doing with a pharmaceutical company in Switzerland. They want to digitalize the maintenance process of their factory. So currently what they do is they have 300-400 pages handbook for the new operators. During the training process, they have to teach all the procedures. They need to follow this strategy with the instruction layer or something. And after you finish each step, you need to submit the data. And at the beginning, there's totally paper-based, but now they are using some apps. But how can we use ontology or use semantic technology to support them? That master project is doing first of all, to extract the knowledge from the handbooks, because a huge amount of the data and the information in the handbook overlaps with each other. Other terms you have to define again in another handbook, for a new system, in a new machine, define again. Many of them they are overlapped. So with the ontology or with the graph database, you can avoid this overlap, and then you can define very precisely what does that term mean and where you can find the information. And then based on this ontology, you can try to, above the already existed databases, trying to check how many steps have you done, and if there's any missing steps, etc. It's very efficient. It's still ongoing, but it's quite missing. And also the companies, they are very capable. It's a simple example.
If I may add something, I'm a scientist. I work a lot with information retrieval and so on. I would be very careful when you're saying you just want to create some kind of Google for your own private
It's like, yeah,
thing.
of course, it's not Google.
Because information retrieval, you have extremely lots of documents you can process, and how you process them. You sometimes just don't care about ontologies. You don't care how the data is structured. You just want to find it. Yes. What you are doing when you are looking through ontologies, you are actually restricting a lot what type of information you are extracting from those documents. Because if you are doing some just to give an example, you're applying very simple NLP processing to detect the verbs in a sentence. Those verbs reflect some kind of relationships. You might try to map those relationships to your ontology properties and relations or whatever it is there. They won't work all the time, or maybe you have ambiguities. What do? If you stay only with your knowledge graphs, you are actually ignoring all that information. So you have to decide now, okay, I have this amount of documents and emails and technical things. What do I get out of them? And I need to be aware of what I'm not getting out of them. So that's why I would take care when I'm saying I just want to find information. I want to find the information. I want to find all information. I want to find some information, so yes. there are really very many degrees of.
That's very quite similar to yours. I hate when my clients say, I would love an interface like Google. Because when you go to Google and you put some words, you recover the information that is indexed by Google. So there are plenty of websites and source that you are not receiving back from Google, and you are happy with that. Yeah. You have some coverage over the domain. But in a company, no, they know that the data is there and they want that data. So you cannot use a Google application. But answer your question, I have a PhD student called Alcides Lopes. And Alcides has been developing a lot of strategies for extracting words and associate ontology. And this is something that can be done in a closed environment like a company. So it's not what you are saying. We indeed index the information that they have, including metadata and models, data models that are like organized tables in the database. In several types of database with different providers is a nightmare. It's not only my group that is doing there. There is a large research group on Book Review, another university, that do this dirty part of scanning the database and extracting the words and so on, and then we provide the semantic part of putting with the ontology, and then indeed we have today a very well covered over this domain, internal document and so on, because they allow us to go through the source of data to extract the vocabulary. It's not complete because they put new information and so on, but it's much better than be asking for some programming guy, oh, please, I need that document to do an SQL for me. So it's not easy to implement much. So there is a lot of hand code to do that, to build knowledge graphs. But it's a solution that is impressive. It's a large company with 50 years of database legacy data, documents, PDF, image PDF. It's a nightmare. But we put together many of techniques, and now we have something better than the other one.
There was a question over there.
Yeah, if you're talking about how you're going to, how we're going to convince some companies in order to use ontology, you have to first understand that you have to make an assumption that they are in a meeting with you to say, okay, well, I want to grow my company. In order to grow their company, they have to understand that they have two main forces that they can be contradictory to each other. Like they want to grow at the same time, so they have to be efficient. And more efficiency for a company, they will bring more complexity. In order to manage these two different forces, they have to use methods and if we don't even use the name of ontology to not make it more complicated, we have to say you need a structure. In order to bring a structure, you have to use these methods. If you want to start on your own company, you want to you want to cook burgers at your in your kitchen, you don't need a lot of efficiency, you don't have a lot of facets in your company. But if you want to become a McDo or McDonald's, you have to have different facets. And in order to change and interchange information within them, you're going to need ontology. You're going to need meta modeling in order to provide structured information during all the different entities that you have.
So I will respond, but some companies might actually say, I don't want a structure. I want to have the agility of a startup.
Yeah.
Okay. I'm not a fan. So yeah, let's.
Yeah. Okay. So this is also some idea from my 3 years study work with Airbus. So we always say in the future, robots will replace people for design, for manufacturing, everything. So why people can do it, robot cannot? Because now for the people in our head, actually we have the meta condition. We know apple we can eat. We know, okay, we can't go through the wall, right? But for the robot, or for the AI, or for the computer, they cannot do it. Because in their head, maybe in the computer or in the software, they don't have a world vision. Okay, what is the world look like? So I think especially when I use the BFO, I think maybe BFO or ontology can provide a chance for the computer. They can understand the world. For example, in the BFO, there's an apple, it's a material entity. So maybe the computer will know, okay, so the material entity apple, maybe someone can eat it, I cannot. So yeah, so that's, I think maybe in the future, maybe years later, so maybe the ontology will be the basic for the AI or for the robot, for the computer to understand the world. Yeah, so that's, yeah.
Is there any questions for the panel?
I just want to make one comment on something that you said. So there's a debate, I think it goes back to a Ryle paper, and I think it was sometime during the Second World War, 59 or 42, I'm not sure. We raised this issue, or raised this question, which she called intellectualism. I'm thinking, I'm just trying to, and it's come back now. There's a recent paper by Stanley Williams, and the issue is whether or not you actually have a model in your mind or not. I have a paper called What's a Concept, where you can find it. I'm not going to read papers references. But the issue is that if you go back to Wittgenstein made the claim that you've got the ability to do something, but it doesn't mean you've got a model in your mind. And I think that links back to the talk I was doing. I think part of what you're doing in ontology is you're creating a model that is the equivalent of your ability to do what the expert can do. I think there's an assumption that when you interrogate the expert, that there's a model in his mind, and you just got to get him to explain to you what the model is, and then you draw it. But I think there's a whole lot of literature and philosophy of mind. Lindsay, I think, talks about it. I'm trying to remember that. It's a while since I wrote the paper. But there doesn't seem to be anything corresponding to a concept. So Locke and Berkeley in the 17th century, the Renaissance, had this early primitive psychology about we've got ideas in our mind, and ideas are pictures. And we translate this into, now we have this, we create these, we've got these UML models in our mind of what's going on. And there doesn't seem to be, there is a tradition in philosophy, particularly philosophy of mind, that says that maybe you just got an ability, you don't have to have a representation in your mind. And I think the philosophers of mind that now talk to the psychologists are saying, look, there's actually no scientific evidence and I do the neuroscience, for us having concepts at all. I mean, and there's a whole series of rafts of issues around concepts. So I think that, I mean, I'm not in a sense disagreeing with you. In fact, I'm giving you an even stronger lever, because it is a case that these experts have got this ability, but A, they can't articulate it, B, they haven't got a picture in their mind. So how do you interrogate them to get the knowledge, to get the ontology, which is what you want? It's even more difficult and even more important.
Yeah.
Okay, so I've got another question which goes in the opposite direction, or following that a little bit. So with every new technology, every new process, we have this madness phase in which a company thinks that's going to solve everything in every context, right? You get agile, and then companies do agile for everything, right? You want to drink water, be agile with drinking water, be agile in the canteen. So have you seen, or do you anticipate, what are the main, I guess, misbeliefs or misunderstandings that companies may have about what they could achieve with ontologies? Well, I think it's good to bound it also, right?
I think, well, if I can comment on that, I think we will live a hype for sure. So we lived it already for different subjects like the digital twin, right? So what was digital twin, blah, blah. So and we see it. So I see it in my ecosystem. So yeah, ontologies. At the very beginning, it was not understood at all. Now it's becoming a little word that people, they know that they need it. They don't know what it is really, but they know that at least something that they want to look at. So I think we will go through a hype on that. Now we as a community, we need to watch carefully and bring this community to teach them. So we have heard that during these days. Now we have to teach the industry, teach the community what can you do, what can you really expect, and not just hype that will bring.
So what is the boundary? What is the things that it cannot? Do you think it cannot do for a company?
An ontology.
Yeah.
What it cannot do.
Yeah. Or when it might not work. In which situations it might not be the best answer.
The best answer is to say to them, explain your problem to me. Don't try to give me the solution.
No. I'm saying in what context you may recommend don't use an ontology.
I think there's an issue about whether or not you can use something like an ontology for something that can't be automated in some sort of way. I mean, if you think the ontology is going to be processed by a computer, so there must be some kind of formal process that you follow it. And I think a lot in your comment that this guy made here about the people who do things now have to be replaced. And Airbus has got this ambition, we're going to replace all these people with robots. I think that there's a whole lot of things that we do that won't be replaced by. I mean, to give you an example, we have the technology of writing and printing, but here we're speaking. This is crazy. We're just using this old technology. Why should we use this old? We should be sitting down here, somehow printing stuff out and then handing it. It's not true. There are different situations.
Yeah, I mean, I'm a technical guy, always thinking from the bottom up. When you have a problem, you choose a solution. So I think at least during this pilot, for example, in Airbus, we have to have very clear requirements or define the stakeholders and what do they want. And also in terms of ontology, I mean, sometimes it's hard to directly to see you can or you cannot use, because even you want to create a knowledge graph, you have different ways to do it. Ontology is one of them. You can use it and visit it, but you can also other ways. And also there are several layers or several steps between ontology and the real problem solving step. So I think always is maybe the ontologist mission to really carefully define the scope of the ontology's capability based on the requirements of the stakeholders.
Any other more questions? Any other questions from the audience? Well, I think we can close it here. We're good with time, I guess. Yeah. Okay. Well, thank you.
Thank you. Thank you.
Okay, so maybe it's time for that. If I say no, I'll be. Okay.
于老师，那就先这样了，今天辛苦您了。
好，学了不少东西。那个我给你发了信，就那个 PPT 可以看一下吗？用一下吗？
我那个到时候我问问他们那几个。
你问问吧，如果要是可以的话，尤其是那个英国的那个 Sorrow 那个还挺好的。
这个到时候我问一下，如果说，但是应该有视频吧，是吧
？AirMeet 上是有视频的，但是您要稍等一下，现在可能还没生成，大概就等一天。
行。
你要是看视频的话，AirMeet 就能买到。
好的。